Thank you for the opportunity to speak here to you today. I'm going to start with a brief introduction, and then I'm going to review what it takes to form carbonated melts and also extract them through a continental lithosphere. Then I will talk about the interaction of these carbonated melts with the lithosphere, and Ottmar has already done some nice introduction on that as well. And then I'm going to finish specifically with a reaction that causes peridotite to be transformed into wehrlite and associated CO2 degassing. And the reason why we care about carbonated melts and rifts is because obviously there is a link between rifts, here in a map from Brunner et al. In 2017, the diffuse degassing of CO2, but also CO2-rich melt volcanism, as reviewed, for example, by Foley and Fischer in 2017. And obviously CO2 is climate active. So the continental lithosphere is an integral part of the carbon cycle. And so when I talk about carbonated melts for the purpose of this presentation, I'm talking about silica undersaturated mafic to ultramafic melts from the basanite, kimberlite, carbonatite spectrum. This is a plot of total alkali versus silica, and Massio et al. Have extended this to include not only basanites and nephelinites, but also kimberlites, which are carbonated silicate melts, and carbonatite proper. And in terms of the tectonic setting, this is just a schematic cartoon, and continental lithosphere varied in terms of disruption. For example, we have proper cratons with intaps, we have craton margins with thinner roots, and we also have rifts, which have in part also cut into cratons in the continents. And the depth to the lithosphere-asthenosphere boundary is important because this LAB gives rise to the so-called lid effect, which means that if you have a decompressing mantle package in the convecting mantle, it can intersect the solidus and form a partial melt, but only until it hits the lithosphere-asthenosphere boundary, at which point decompression melting stops. And so that can keep the melt fraction low, which is important, as we will see in a moment. So to form carbonated melts, two conditions must be met. One of them is you must intersect the solidus. That sounds trivial, but it's not so trivial in the continents. And you also must allow for the stability of oxidized as opposed to reduced carbon. And here, oxygen fugacity comes into play. So this is a plot of oxygen fugacity relative to the phyllite magnetite quartz buffer as a function of depth. This is from Stagno et al. This is basically for oceanic lithosphere, which is decompressing. It has about 4% ferric over total iron. And as it decompresses, it becomes less reduced, more oxidizing. And eventually it intersects this reaction, which is the redox melting reaction. And then about 30 ppm of carbon in the source will be oxidized to CO2. And some amount of that ferric iron will be reduced, and the remaining parcel then goes on this path here. What is interesting in terms of continents is that this reaction takes place over a depth interval of about 150 to 120 kilometers. And so when you see carbonated melts, such as kimberlites, in thick continental lithosphere, it probably means that they come from a source that is more oxidized than the ambient convecting mantle. The other condition is that you want to limit dilution with silicate components. This is a plot showing CO2 concentration in the melt as a function of liquid fraction. And on the right, it's CO2 versus silica content. And you can see that if you increase the melt fraction, your CO2 content decreases. And this is because CO2 is highly incompatible. It goes into the melt at the first instant, and then continued melting will cause its content to be diluted while the concentration of silica increases. So if you want to have a carbonated silicate melt or even a carbonatite, you must keep the melt fraction low. And for this, it helps actually to have thick lithosphere or great depth to the lithosphere asthenosphere boundary, and this shows pressure versus temperature. You can see the dry peridotite solidus and one for peridotite with some water in it. You can see that in the cratons, it's not easy to intersect the solidus. You must have high temperatures, mantle potential temperatures, and then you can intersect this particular solidus and form a small percentage of melt. Whereas if you're in a rift setting, the depth to the LAB is shallower. You can intersect this solidus easily, and you can decompress even at ambient potential temperatures, and you decompression melt again until you hit the lithosphere asthenosphere boundary. And you might in both cases avoid strong. Now we have made a carbonated silicate melt, but we also need to extract it through, say, 100 to 150 kilometers of continental lithospheric mantle. And this is again not trivial, because this mantle, when it forms, is reduced and depleted, and it's also cool. And this presents a chemical thermal barrier to put a carbonated silicate melt through, for example, and much less carbonatite. I'm gonna switch off. Can't right now. Okay. So when you look at pressure versus temperature, you can see here again the two solidi I've shown you before, and you can see a typically cratonic geotherm, and you can see also some actual samples. Thank you. For cratonic lithospheric mantle xenoliths, and you can see that they are well below the solidus, so there's no melting here. In addition, when you look at oxygen fugacity constraints, this is the plot I've shown you before. Oxygen fugacity as a function of depth. You can see the stability of diamond versus graphite as opposed to carbonatite or magnesite. You can see that the vast majority of lithosphere is actually not stable for carbonatite, pure carbonatite, but it might be stable for a carbonated silicate melt. So these are some limitations to instant extraction of carbonated melt through continental lithosphere. When we go to rifts, which might have cut and already rejuvenated cratonic lithosphere, we can see that we have much higher geothermal gradients, and we also have higher oxygen fugacities, which allow for the stability of CO2 or carbonates. And so the idea is that because of this initial disequilibrium, both thermally and compositionally, that there's strong interaction between carbonated silicate melt and the cratonic lithosphere. And this gives rise to a reaction, which is the inverse of redox melting, it's redox freezing. And so basically we drop carbon in the form of a diamond, oxidize some iron in return. And we can look to the diamond record for some ideas on how this refertilization and reoxidation that eventually allows for increasing stability of carbonated silicate melts has occurred through time. And so we know that the oldest Harzburgidic diamonds formed about 3.5 billion years ago. We see from the Proterozoic onward, however, increasingly lursolytic diamond formation. And these are suggested to have formed via this redox freezing reaction, which is accompanied by oxidation and refertilization, so the formation of lursolite. And so this idea is that there is some sort of lithosphere conditioning occurring, which prepares the continental lithosphere for eventual successful eruption of carbonated silicate melts. And this is shown schematically here in this cartoon at the bottom. In contrast, when we go to thinner lithosphere, continental lithosphere, such as in rift settings, what we frequently see Wehrlite xenolith as part of peridotite xenolith suites. And so this is a different reaction that these are testifying to, which is the decarbonation reaction, which forms to the formation of wehrlite and CO2. So we have enstatite plus dolomite going to olivine, diopside, and CO2. And this leads to the formation of clinopyroxene and olivine-rich peridotites fading into wehrlites, which we can also see when we look at the modal composition of some of these xenoliths. This is an example from the Tanlu fault belt. Tanlu fault belt, yes, which is a giant translithospheric fault in the North China Craton. And we can see how the samples have evolved away from the OPX apex towards the olivine clinopyroxene apex or line. And we can also sometimes catch that reaction petrographically. You might not be able to make it out, but we can see how a CPX forms at the expense of OPX, exactly corresponding to this reaction. And then we can look at various wehrlite-bearing xenolith suites from around the world, and we can see that the clinopyroxene modes increase, and sometimes that is accompanied by an increase in calcium over aluminium, which we then typically ascribe to carbonatite metasomatism, so a silica-poor carbonated melt, whereas sometimes an increase in clinopyroxene mode gives rise to higher FeO contents, which is probably a more silica-rich melt that has caused the wehrlitisation. And the interesting thing is that we form a CO2 vapor. And so what we have done is we've applied this decarbonation reaction to xenolith suites from around the world to estimate the amount of CO2 that has passed through the shallow lithosphere. And this is a table from a recent paper which lists these different localities. We've identified various agents. We've estimated the amount of diopside that was formed, the mass of enstatite and dolomite that was converted. And in the end, we come up with an amount of 0.2 to 2.4 kilograms of CO2 that were released per 100 kilogram of peridotite involved in the reaction. And when we then actually weight that by the area estimate and the estimated duration of the wehrlitisation event, we come up with fluxes. And here I would like to highlight two, which is again the Tanlu fault belt, where we can see that a flux of 70 megatons per year total has been generated over about 30 million years. And when we look at estimates from a Brun et al. For the Mesozoic CO2 high, we can see that there are amplitudes of up to over 80 megatons CO2 per year. And so it looks like the Tanlu fault belt could have been a major contributor to the Mesozoic greenhouse climate. And then I want to take you to the East African rift, where we've estimated 6 megatons per year of CO2, about 44 million years. And this estimate is actually, given the uncertainties, it's quite similar to the 6 to 18 megatons CO2 per year that were made based on sufficient to be derived from the mantle. And so I think this similarity in estimates provides a really convincing link between degassed mantle CO2 that we see at the surface and the CO2 forming mechanism that occurs at depth, which is wehrlitisation. And with that, I want to leave you with the summary, and happy to take questions if there is time. Sorry for my unstable internet connection.
Thanks, Sonja. There's quite some time. So if you have a question, please type it in the chat. And we could understand almost everything. There were some concepts, but otherwise drop and learn.
All right, sounds good. I can't see anything in the chat yet.
Yeah, so no, people are probably just typing. Okay, there's the first question. Abdul Kadir, could you ask it, please? We can't hear you.
I can say, well, he's asking, is there a possibility that carbonatite melt is generated in the crust? I think this is possible, but I am not a specialist on this. I'm more interested in the generation of carbonatite at mantle depth, but I believe in general it is possible, yes.
Otmar has a question. Maybe you ask it yourself.
Okay, thanks, Sonja. I just wondering when you compare that one area is a very good place to produce a lot of CO2, which was postulated in Sascha Brune's model. Do you have an idea over which time scale the CO2 went down to carbonate all these prototypes?
Yes, actually, we're not at that stage yet. So the paper last year was just the first basically attempt to even see if we the quantitative estimate is that we're not limited to looking at tectonic rifts, such as the East African rift, but we can look at through time to see if we can estimate how much was degassed over time via rifting in terms of CO2 coming down. I think that is probably more strongly linked to elevation, mountain building, and so on. If I got your question right.
No, maybe I could reformulate it. When you take the ICDP drilling project in Oman or others, they think a lot of CO2 that is recycled comes out very early and doesn't go really to the deep mantle. Does this influence your overall carbon budget?
Oh, I see. I think personally that there's a lot of scope for CO2 to be deeply because we see in guides that former oceanic crust through time that they are very reduced and they are not at carbonate stable conditions. So we have formulated the hypothesis that actually diamond formation in subducting oceanic crust through time could have been an efficient carbon regassing mechanism. So I think probably more goes down, and some even went down in Archean time. And Archean eclogitic diamonds, which formed at the time of continent collisions, so strongly linked to actual tectonic events, are probably a testament to that, in my opinion.
Okay, thank you.